I want to welcome you to the architecture of a geo-distributed SQL database. My name is Lindsay Hooper. I'm one of the Postgres conference organizers, and I'm going to be your moderator for this webinar. I'm here with Jim Walker, VP Product Marketing at Cockroach Labs, and Chris Casano, Solutions Engineer at Cockroach Labs. Let me tell you a little bit about them. Jim is a developer who spent a large part of his career helping people understand complex emerging technologies. He's passionate about distributed systems, data, and open source technologies. He's a startup-aholic and loves building apps in new communities, and he has helped build companies like Hortonworks and CoreOS. Chris, prior to Cockroach, was a senior solution engineering manager at Cloudera, a solutions engineering manager at Hortonworks, and a principal sales consultant at Oracle. Welcome, Jim and Chris. We're super excited to have you on the line today. One quick logistical note for you. I've put you all on mute to avoid background noise, but we do still encourage you to ask questions. Questions will be answered towards the end of the training, though pressing one should be answered in the moment. You can ask these questions through the chat function, depending on what kind of computer you're using. That chat function is either going to be at the top or bottom of your screen. With that, I'm going to hand it off to Jim and Chris, and you guys can take it away. Enjoy.
Awesome. Thanks, Lindsay. We are excited to be here with everybody today. I hope everybody in the audience is healthy and staying safe. These are some interesting times, but we're excited to talk to everybody today. I'm excited in particular for this webinar. Actually, we do a fair amount of them at Cockroach Labs. Because I think, the Postgres world and being part of Postgres and that community, I've been definitely involved in it, building on top of Postgres for a long time. I'm just so amazed at how big and vibrant the community is. And so we're excited to talk to everybody today about, what is a cloud database and what do these things look like over the next couple of years, how we think about scale, how we think about resilience, how we think about meeting the expectations of our users no matter where they're at. And that's globally. How do I, have like a great experience for everybody? And I think that's, one of the challenges around applications is really data and transactions and how we meet these kind of diverse workloads. Marv Adrian is an analyst at Gartner who I look up to as somebody who I feel is a pretty smart, great analyst, and he believes that the future of all databases is cloud. And I kind of agree with the guy. So that's kind of a quick intro. So why another database? We have relational databases. You're all obviously familiar with Postgres. You kind of know there's NoSQL databases, the things like Mongo and some of these other things like Cassandra and some of these other databases. With the inception of cloud and with kind of the requirements to scale, the requirements to be resilient, and really kind of with distributed systems, there really is an opening for a different way of thinking about a database and not taking legacy systems and making them fit into distributed systems, but let's just build a database that was really from the ground up architected for distributed systems. And that's what we're doing at Cockroach Labs, and that's what we've been working on for a fair amount of time, really since the start of this company, 2015. And so we fit. And if I think about relational workloads, some of these kind of transactional system of record type workloads and applications that we're building, as they move to the cloud, having a database that is not only SQL, but will scale and build in this resilience is kind of critical. And really kind of what we focus on. Lots of people find Cockroach Labs because of, they are building out kind of a microservices-based platform or application. They're breaking down a monolith into these things. And so if I think about this, like the traditional way of thinking about a database, if I think, back in the days like Oracle, the way we would get redundant systems and get coverage, like global coverage for a database is, we have instances of Oracle, we use Rack, we use Golden Gate, it's bulky, it's costly, it's difficult to get going, right? I think AWS has done a good job about pushing forward into kind of cloud database. The problem with AWS and Aurora is it's not really a cloud database. It wasn't really built to be a distributed system. I think distributed storage is awesome, but in a true kind of world of distributed systems, what we think of typically is shared nothing. And that's something that we've gone a long way to actually have this kind of more matrix type database where each instance of CockroachDB is its own single atomic unit, is its own kind of standalone piece that coordinates and takes part in a larger system. We don't live on top of anything that's shared. And I think that's one of the things that allows us to be a truly distributed system. And I'm going to go into how we did that in this webinar today. That's what we want to talk about. Like, what does it mean when I say, don't take legacy tech and move it to the cloud and try to make it kind of distributed? What does it mean to actually tear apart a database and think through, like, how do we become a distributed database at the core? And how do we build something from the ground up to be so? For me, if you're going to be a distributed SQL database, and I think about this as kind of a new emerging group of databases, well, number one, and I think everybody on this phone would agree, you've got to speak SQL. Like, I'm not going to require y'all to go out and learn a new language. I find it incredibly important that we should be able to use the interfaces that we have today. You know, we're wire compatible with Postgres today. You can use, you know, there's a world of ORMs that we've built if you're into that, if you like to use ORMs. And we're going to work the way you work today. And I think that's actually really critical. Requiring people to learn something new is not realistic. I think, you know, our application speaks SQL today, and I think, you know, gosh, I was learning SQL a long time ago, and I think it's still applicable today. You know, a distributed database should ease operational scale. I think we can shard databases. I think probably a lot of people on this phone today have gone through this whole manual sharding process. It's difficult. There's a lot of operational overhead. Distributed systems should automate scale. And so how do we make that happen in the database? That should be a requirement. These databases should be always on and resilient, right? Another kind of like a core tenet of distributed systems. And if you're going to be a database and you're going to store data, well, you can't lose data, right? That's kind of important. So you got to be ACID compliant and allow for transactions to happen. We, for instance, we implement serializable isolation. So this isn't like snapshot isolation and eventual consistency. This is true consistent transactions. Difficult to do in distributed systems, but I'm going to show you how we do that as well. And then this last requirement for a distributed database is tying data to location. Now, sounds simple, but it's really difficult. Typically, as application developers or people who are dealing with the database, will actually build a layer at the application layer to basically tie data to location. So all records of this type can only get stored in this set of servers that's typically left to the application layer. If you're going to do that, you know, we believe that that should be part of the database itself, because ultimately, if you're going to be a distributed database, you're fighting against the speed of light, because, you know, latency between data centers is no joke, right? And if you're going to do, you know, if a transaction takes, you know, 4 different phases or 10 phases, and it's got to go back and forth between 3 servers and 3 regions, you know, latencies add up, and, you know, users are not going to wait, you know, more than, you know, 100 milliseconds or 200 milliseconds for a transaction to finish. So, you know, tying data location is actually really important from a performance point of view to give the right experience for the people who are actually accessing that data, for the users of your applications. You know, we like this because it allows us to do things like, you know, we have a feature called Geo-partitioning. It allows us to basically tie data to location to also meet, you know, privacy requirements as well. But I think it's a nuance that this is really about performance and really a critical thing. And so how does the database automate that? Now, again, CockroachDB, this is a unique architecture, and starting at the top level, each instance of CockroachDB, I could spin up an instance right today on this laptop that I'm working on. I could point it at a cluster, and it's going to participate in the larger cluster. Every node in the database is a consistent gateway, or an endpoint, if you will, right, to the entire database. It's actually pretty important, right? So while the data is going to be stored in triplicate across multiple different nodes, and we're going to show you that, like, I can ask any node. I could have 1,000 nodes, and it's going to know where to find that data, which is kind of cool, because I could spin up a node here. I could spin up a node in AWS. I could spin up a node in Azure or GCP. And actually, I'm going to have one database, and every node is going to have access to all the data that's living across all those nodes. And that's truly a shared nothing experience, because I have the complete instance, the complete binary is the same at every single node. And, you know, we've gone a long way to build out all the management and optimization of this thing. You know, all the enterprise security capabilities you need. You know, we actually built a location-based, cost-based optimizer. So familiar with that and how to actually, you know, tune performance around CDO. We built that actually into the database too. It's kind of cool. Now, where it gets really cool, CockroachDB is this unique distributed architecture that, because all these nodes are their single, you know, atomic unit, they actually coordinate with each other so that we can actually coordinate transactions, because we're going to write data in triplicate, and I'll show you how we actually coordinate transactions. But if a transaction comes in Sydney and a transaction comes in at New York on the same record or the same row in a database, who wins? The database actually deals with those conflicts and ensures that you're going to have no overlap, right? Ensures you're going to have serializable isolation for things like that. And so it coordinates for that, but it also coordinates in that there's no more manual sharding. If you want to actually expand the database, you just keep throwing nodes at it. The database is going to worry about basically spreading that data out in an intelligent way so that we can actually deal with performance and utilization of servers and whatnot. And then again, we can attach data to a location because of performance and because of privacy concerns and this sort of stuff. So lots of cool things that we're doing here, but let's get into basically now the architecture of how this actually works and the differences here. And so, lots of databases are databases, but some databases are actually built on other databases. And, sounds kind of meta, right? But, we actually built a database on top of a KV store. So if you're familiar with KV stores, a key value store, underneath the covers here, we actually use a database called RocksDB, and that's between us and the storage layer, because every database can be broken down into the language, the execution layer, and the storage layer, right? And at the storage layer, we're actually using KV to store data to disk. And it's actually pretty important. It allows us to do some really cool things. We've completely re-architected the execution layer to do all this coordination. And then we've also, we made sure the language is SQL as well. So across these three things. So let's just start with every table. Every table in CockroachDB can really be ultimately at the storage layer, thought of as this monolithic logical key space. And we order everything in here. Here's a dogs table, if you will. And we're just ordering everything by name of dogs. So you can see it's basically in alphabetical order here. And so basically every table ends up getting that looks like this. Now it's a little bit different. A typical database, you just keep adding records to the table, say it's an inventory table. And in order to find these things, we set up indexes. There are other tables that actually are meta and allow you to do some things. We don't need this because we're actually ordering everything based on key, right? So the keys are all ordered in CockroachDB. So it's a little bit different from the typical database structure, which you're going to find in Postgres and some other things. It allows us to do some really, really cool things. Now, the SQL, the problem with this is that's KV. How do I deal with tabular data, right? How do I deal with this relational data so that I can actually run queries like that I select star from customer? That's a little bit different. And so the traditional way of looking at a table needs to be translated to the kind of KV layer, right? And so we do that. This is part of actually, if you're ever looking to solve insomnia, right? Like you go read the white paper about Google Cloud Spanner. I think this is one of the really cool things that, Spanner really led the way with, and the designers there that really dreamt this up. Really cool stuff. And this is really what allows for this distributed nature of our database. So the Google Cloud Spanner actually, that white paper that lays out a lot of this stuff. So at the KV store, what we're actually doing is we're going to translate that stuff all up into SQL. This allows us to do some really cool things. It allows us to efficiently distribute data. It allows us to do dynamic schema changing, and allows us to do this really cool thing around geo-partitioning as well. But I'll show you all that, right? And so let's just think about a table. Here's our dogs table. It has three fields: ID, name, and weight. Typically, table entries kind of look like this. Now, what we're doing at the KV layer is we're actually translating this when we store the data. This is the way it looks on the right-hand side. This is how it looks at the execution layer, right? The SQL execution just thinks about it as a table. But at the storage layer, we're doing something kind of cool. We actually we're going to each take each one of these rows, and we're going to break it down so that the key, right, is going to be basically an index, right? It's going to be the table name, it's going to be the ID, and then the column that I want to store. So in this case, it's the dog table, ID number 34, and name, and the value is going to be Carl, right? And then weight is going to be 10.1. So where I had one entry where I was storing in the traditional way at the storage layer, here I have two entries. Now, this allows us to do cool things because we can actually change the primary key. You know, we can do some interesting things in this key, like this 34 can actually be a consolidation of multiple different fields so that we want to order things. But ultimately, if you look at this, we can just order these things. And now I know exactly where to put the next record in here into this table. And the KV is what allows us to basically keep this completely ordered pair of key values that are going to translate back into the SQL table. So this is actually a really kind of cool trick of what we're doing here. I'm not going to go through this example, but just think through how we sort things in say Excel sheets. You know, I could sort on one column, and I sort on the next, and I sort on the third. We actually can like embed this sorting. So this really kind of cool way of sorting data that allows us to do some really cool things, right? We have this monolithic logical key space. Now, we take this key space, and what we do is we break it up into 64 megabit ranges. A range you could think about as a shard. And instead of us having to kind of manually choose the shards, the database is just always doing this, right? It actually is always thinking about the ranges. And we're going to use Raft, which is kind of cool concept too, to actually show how these things get then distributed, right? And so here we have this table. We're going to break it down to 64 megabit ranges. Here we have just 3 ranges, right? They're small enough so that we can move them around quickly, and we can split them. But they're also kind of the right size so that we can actually gain value in terms of how we index them and how we think about them. So if we're going to break a table down to this, we actually need a layer that kind of allows us to understand where to find things. And we're just going to update this thing every once in a while as we kind of add more table and more data to this basic monolithic key value storage. This is very much like a B tree, right? If you're familiar with that concept. So order keys, they allow us to do cool things. Like we don't have to do these crazy like table scans. We're doing these very efficient range scans. So if I wanted all Dougs between Muddy and Stella, underneath the covers in the database, it knows it only needs to go to these 2 ranges. Now these ranges are going to be physically stored on different servers. And so this actually allows us to be very efficient in how we use network and bandwidth. And the various different servers that are in this thing. It actually really, really key concept, especially when we're thinking about distributed systems. So what happens when I want to insert a record into a table? I want to insert Sunny. That's my friend's dog. So I'm going to put Sunny in there. Sunny's going to go, let's see, in between Stella and Z. So I'm going to ask that range. Do you have data? You have space? Yes, great. Let's insert that record. We're going to insert that record. It's going to be updated in a couple different spots. What happens when I want to insert and there's no range? Well, underneath the covers, what happens is CockroachDB actually automates the creation of a new range, right? We've split that range in 2, and we now have more extra space, so we can actually go ahead and insert that record into that range. Now, we aren't doing this in real time. We actually will allow a range to go a little bit over in real time, and then come back and actually fix all this stuff. So we don't affect performance. Like I don't have to actually split the range while the transaction is happening. I'll just note that, hey, this range is a little bit full. I better split it. Great. And so this is where we get this whole sharding capability, right? Like, and I'll show you how we're writing data to the various different nodes, but think about what this means now from the way we think about like shards and manually doing this process. The database is just doing this, right? And so no more manual sharding. It just basically automates this whole, like we just split ranges, right? And so a new range index was created, order was maintained. I could find that data. If I delete data, it'll actually consolidate ranges together. So it'll actually retract as well. So it will both expand, and retract the database too. And so that's a really key piece of what we're doing here. And that's underneath covers, unbeknownst to the developer. The database is just dealing with all this stuff. And it ensures basically this easy scale and kind of resilience. Now, when we write data into the database itself, like we're going to actually write on physical nodes, like physical locations. Like, so I'm going to write, I'm going to have a cluster with 6 nodes in it. Those are 6 different machines, if you think about, and I'm going to actually write data 3 times. Like by default, the database is going to write data 3 times. There's going to be 3 replicas of each of the ranges. So here we have 4 ranges. We're going to actually write the first range, Carl, Downey, Figment, and Jack. We're going to write it 3 times across 3 different physical servers because we want to survive certain failures, right? We want to actually distribute this data out in a more comfortable fashion. We use something called Raft to do this, and a Raft group. A Raft group basically takes these replicas, like that first range, there's going to write it in 3 ways. And that little group, they communicate with each other and make sure everything's cool, right? And they're really what ensures that like there's this atomic replication of commands. And atomic replication basically says like for that group, one thing has happened. Like, you know, it's like an acid, you know, A is atomic, like, you know, that atomic unit, that happens for that group, right? And there's this concept called a leaseholder. You might hear of, like, if you know Raft, like it's a Raft leader. That's the unit that basically in this group of 3 copies of this range, they actually understand really what's going on. They're like the leader. Most things go through them, and you're ensured you're going to be right. But they basically kind of coordinate everything for each Raft group. So in the implementation of a database for CockroachDB, Cockroach database, there's thousands and thousands of these Raft groups going on, and lots of coordination going on amongst all of them. So let me just, I'm gonna fast forward a little bit just because of time and get into the stuff that's really important. So that actually, I'm gonna have Chris show you guys how this actually works in the database. But when we write data, here's our table, right? Our dog table. We're gonna actually write it to physical locations. So here we are, like, this is what I was just talking about. The Carl through Jack range, that shard is being written 3 times across 3 physical nodes, node 1, node 2, and node 4. You know, range 2 is going to be written on node 1, node 2, and node 3. Range 3, node 2, node 3, node 4. Now, what we've done here is we've actually distributed the data across physical nodes, the replicas, so that we can actually survive certain failures. I want to survive failure domains like a disk or a rack or a data center or a region. We can tune the database. Actually, you can use a command called alter table, and we can actually change this in real time in the database. And the database will actually change where all this data lives, so you can fail different things. But it really depends on what you want to do. When you implement something like Cockroach Database, you got to think about 2 things. You got to think about latency and resiliency. What do you want to? What kind of failure do you want to survive is a key thing when you're thinking about the table itself, and then, you know, what is the latency? Do I need data to live in certain locations? I'm going to show you how we do that as well, right? And so we're going to distribute on this sort of thing. So if you think about this, well, this is kind of to even out storage, right? And utilization of disk basically across the cluster. We basically wrote the same amount of data on every single node. Sometimes a range, however, is accessed more than other parts of a table. And so the database is smart enough to also understand that utilization of each node is actually really important. So I can isolate a range into nodes that have, you know, that are straightforward for a particular utilization, so that that workload is going to have the same performance or optimized performance because I've placed it in an area where there's not a lot of other ranges, right? And so I can basically take heuristics of how that data is being accessed. You know, Muddy is a really popular dog. That's my dog. Obviously, she's really great. And I'm going to actually take that blue range there and I'm going to put it on nodes without a lot of other data so that I can optimize from a load point of view too. And the database is automatically doing this underneath. So not only are we placing data based on load, but we're, you know, by utilization of storage, but we can do it by load. Now we can also do it by geo-partitioning. So the same concept that we had here. Here, what I've done is I've actually overloaded the key with a value from the table for location. So you know, you can imagine that table had an added column for country or whatever that is, or location. Here's the EU, US East, US West. And so now these shards or these ranges are going to be tied to servers because each server, each node is tagged with the location. And so we can actually geo-partition data as well. So not only can we distribute data to survive failure, not only can we distribute data to work through utilization issues, but and access and workload, but we can also do it from a geo-partitioning point of view. And all of this can be changed on the fly. We can actually change the primary key. We can change this key, the K and the KV store. And so that once we change it, the database is going to automatically start to move things around and make it correct for everybody, right? So kind of cool thing about what we're doing here, and kind of unique and important because it actually sets up some of the key capabilities of what we're doing. So really quickly before the demo, again, we can rebalance replicas. So here we had a 4-node database, a 4-node cluster. We just introduced a new node. The database is smart enough to actually just start moving data around to balance things, right? And so I just, you know, it writes the data, recopies it in the new node, and then actually decomposes the previous replica yet Raft still maintains the connection between all of those replicas, each of those shards, if you will, right? And so that's kind of done, and we just take care of that. We can actually survive a failure as well, right? So often a node will go down, and Chris is going to show you this in a demo, right? Here we have node 3 went down, and it had 2 replicas on it. Each of those replica sets is smart enough to understand that's like, wait a second, I'm missing one of my replicas. I've got to have 3. Like I can't live without having 3, man. Like, what am I going to? So it's smart enough to actually understand, like the leaseholder is going to say, wait a second, I don't have a 3rd replica. Let's create a 3rd replica on a node that's available, and make sure that I have that in the database. So you'll see something in the demo, like under replicated ranges is what we call that. And that's really when a node fails, the replication factor has gone down to 2 for a moment until the database can actually recover from that. But all the while, any one of these nodes, because each one of them is an endpoint, could have taken that query and found the data no matter what, right? So you're never going to lose access to the data, right? It's active mode. We don't need active passive in the world of this. We can do distributed backup and restore for those sort of things, for those kind of trouble issues, but we don't. There's no more like active passive system where if it fails and I bring the passive system online, and that thing's going to run for a while, and then basically I bring back up my original primary, and how do I actually consolidate records across these 2 databases now? That's tough, man. Like those problems, that RPO, RTO issues that people typically think through, just doesn't happen with us because everything is active, right? So this really simplifies a lot of things from an operational point of view for developers, right? It's going to be SQL number 1, so that's great. But this whole this sharding thing goes away, the resilience thing kind of gets solved as well. And so we can also survive a temporary failure. So it isn't as harsh, but I wouldn't. So Chris, do you want to jump in and just show a little bit about the resilience and the scale part of CockroachDB?
Absolutely. Can everyone hear me okay?
I can hear you just fine. And then, by the way, everybody, there is the chat window. I am monitoring chat. So if there's any questions, do please feel free to do that there. So Chris, I believe you have the floor.
Great. Hey, everyone. Good morning, good afternoon, good evening. Good to meet you all. I'm going to go through a quick demonstration really around the fault tolerance of CockroachDB and how you can maintain performance by being resilient. And you can repeat this demo if you'd like. If you go to our website, docs.cockroachlabs.com, we have a section over here called tutorials, and there's some great tutorials on how you can learn how to use the database. The one I'm going to go through today is around fault tolerance and recovery. What we're essentially going to do is stand up a 6-node cluster. I actually already stood it up, so we don't have to spend time. You see me set up things in AWS, but we have a cluster set up. We're gonna give it some workload, and then we're going to start removing nodes. And I'm going to show you how the replication factors work. I'm going to show you how the resiliency works while maintaining performance. Okay, so let's go over to the UI. And you're actually going to be seeing some new bits here too. So I'm actually showing this within one of our beta releases. Usually this is a solution engineer no-no as far as demoing things on new software, but I've tested this out a couple times. It works great. So I wanted to show you some of the new things that are coming within our next release, which is the 20.1 release, which you should be seeing hopefully towards the end of this month, maybe if not beginning of next month. Okay, so here's the administration UI. You can see I have 6 nodes that I've created in the database. If I go to the metrics section, you can see that I actually already have some load going on here. All right, if I look at the SQL queries, you can see that I have a lot of selects and updates that are happening. And over on the right-hand side here, it's giving me an idea of the queries per second that are being performed under the current cluster. There's other things I can look at too. Yeah, Jim, go ahead.
Hey, Chris, what's the workload that you're running right now?
Oh, yes, this is the YCSB workload. It's the Yahoo benchmark. So we packaged a bunch of different workloads within the database. The one I'm showing today is the Yahoo benchmark. And if you want to see it running.
But with the database, yeah, with the database binary itself, there's actually a couple of different workloads that people can use to test out the database as well, right? So that's all in docs, is I guess where I'm going.
Exactly. I can even show that to you. If you can just do a search for workload within our documentation, it will take you right to Cockroach workload, and you can use a variety of workloads here, such as TPCC. A lot of folks are definitely familiar with that. There's a whole bunch that you can run there. But anyways, yeah, I'm running YCSV. You can see we have load there. We can look at the hardware metrics too. You can see that we have a lot of CPU utilization. The nodes I'm using are actually kind of small since this is a demo environment. But you can see that we have workload happening. Now, what we're going to do is, if I go back to the overview, you can see we have 6 live nodes and we have 51 total ranges. What I'm actually going to do is I'm going to actually remove one of the nodes and we can see what's going to happen with performance. So let me come over here. I'm going to do a little command, say stop a particular node on my cluster. I'm going to stop node 6. And I could have done this more crudely as well. I could have, logged into the machine, do a kill command, and it'd be a little bit more abrupt. I'm going to do this more in a gentle fashion. So as you can see, I stopped the node. You can see the node is under suspect here. I have one node that's the cluster identified as not being available. If we go and look at the metrics, there is a little bit of a dip, but you're going to see this come back up, and the performance will maintain. And on top of that as well is that you'll notice that the database is actually very patient, right? So we have a couple different statuses here. We have a healthy status, we have suspect, and dead. We're actually, because we can't communicate with a node, we don't just eliminate it from the cluster. We'll wait for it to come back. There's a default time of about 5 minutes where we'll mark something from suspect to dead. But if the node does come back up, it will just reapply itself to the cluster. And that's what I'm going to do here. I actually set this command actually to mark a node dead after about 1.5 minutes. So I want to get it back in there. And what you'll see is that eventually these ranges that look like they're under replicated are actually going to go back to being replicated because I just added that node back into the cluster. So, in just another second or so, you'll see everything be healthy. Now, right now I'm running this with a replication factor of 3. So, I can tolerate a single node failure. If I want to just tolerate more node failures within my 6-node cluster, I would need to up the replication factor. So that's something that's pretty easy to do, and you can do this even on a live database. So I'm going to show that here, where I'm going to come in and I'm going to change I'll show you this command in just 1 minute. It's basically an alter command that Jim was mentioning before. Actually, no, before, yeah, I'll run this and then I'll show you what this zone configuration is. So what I'm going to do is there's a default zone configuration, and you can change this to specify how you want things to replicate, what your ranges want to look like. If you want your ranges to be in certain regions, or the number of replicas that you need and have an affinity towards a certain region, you can do that within this database. So I'm going to kick this off. This is actually going to up the amount of the replication factor to 5 within the database. And you'll notice here in just a few minutes, yeah, you'll see that I'm actually under replicated, right? Because now I only had 3 replicas and I need to up that to 5. So the database is aware that, hey, this configuration change was made. It's going to identify the ranges that are under replicated and start moving them out into the other different nodes. So you'll even see here that like the number of replicas that you're seeing in the nodes are going to go up as well. So we'll just give this another minute or so that we get into a healthy state. And then I'll show you how we can eliminate 2 nodes and still have the resiliency and performance under load. Does that make sense, Jim? Any questions coming so far?
No, either like we're that good at explaining things or we bored everybody to tears. No, I'm joking. No, it's pretty straightforward because this is awesome.
Yeah, no, it's good. You can see here we did have a little bit of a dip, but everything was went back to as right as rain. During the node loss, and you can see here that the service latency or the node fell out of service during that time. So let's go back and check. So yeah, we have about 1 more range to get cleaned up, and then we're gonna do the same thing. We're gonna eliminate 2 nodes, and we'll see how the performance looks. While we're here, you can see we're good. We're in a good shape. While we're here, there's other things that you could do within the UI that are actually really useful for diagnosing things that are happening or monitoring activity. You can look at latency of statements. You can look at the jobs that are happening in the database. You can see there was an import job that was run here to actually seed the database with the workload that I'm running. And there's a lot of advanced debug features. There's a really rich REST API that we have so that you can see a lot of things that are happening within the database that all power this this UI. Okay, so last part of the demo, let's go just do, now that my replication factor is up, I'm going to stop 2 nodes. Let's stop node. We'll stop node 6 again. And we'll stop node 5. And because our replication factor of 5 is up, you know, we can incur a 2-node failure. And again, you'll see that we have two suspect nodes that are here. And the metrics, we'll go back to that as well. You'll see that pick up eventually as well. And what we'll do too is we'll actually have one node go into a dead state, and I'll actually bring back one of the nodes so that you can see what's happening here. I know we're getting a little bit tight on time, so just give this just a second.
Chris, take your time, man. People like to see, people don't like listening to me, dude. I'm just a slide guy. Like, this is much better, buddy.
Cool. All right, well, I'm gonna bring back node 5. Just so folks can see this happen. You know, we kind of saw this in the last scenario where we have a suspect node that's going to come back and be attached back to the database. We'll see that suspect nodes go from 2 to 1. So we have 5 live nodes, and I'm going to let that other node just die. And you can see how you know, the database will continue on and continue to perform. My workload should be going for another couple of minutes, so we should be fine here. But yeah, after about a minute and a half, you'll see that this node that's in suspect will actually go to dead. That's pretty much it. I mean, that's all I really have to show from a performance perspective. But it's just a very patient database in dealing with adversity. So when you do have failures, disk failures, node failures, and so forth, it takes a pause. It looks at what's going on, and then it, you know, patiently will say, all right, you know, I need to replicate over here, or I need to balance myself out so that I can continue to meet the workload that's being asked for me to do.
Yeah. So Chris, a couple things. I think it's really cool. Like, look at this service latency. The 99th percentile for P99 latency has actually gone up as you made changes. Another key thing, right? You know, we're constantly looking at P99 latency. That's one of the things we're looking at. Actually, 23 milliseconds is pretty high. We can do lots of things to actually get that even further down. There's lots of tuning. Typically, we're seeing those things under 5 milliseconds, right? And so I think there's a lot of rich stuff in this UI. One of the questions that came through, Chris, was how do you run multiple nodes with the web UI? I mean, is there fault tolerance for the web UI? I guess, like, how does the architecture of the web UI work, right? Like, somebody asked me, is this part of CockroachDB core? Yes, this is definitely part of the free version of our database. You can download, you can actually be up and running with this. Like, I can do it today. But how does the web UI architecture work? Like, where is that running? Is there multiple instances of this? Like, how does that, what's the fault tolerance for that?
Great question. So since we're shared nothing setup, you can run the admin UI on any of the nodes. So, you know, if one of your nodes dies, you can easily just connect to another node and spin up the admin UI. There's nothing you really have to do from a setup perspective to make that happen. It's not like you have to, think about my application being on two different management nodes, make sure that they have a shared database to have all the metrics and so forth. It's a much easier setup. You just basically say, I want the admin, UI running on this node. If that node dies, I can just spin it up on the other node, and you're off and going.
Right. So a node is a node is a node. It's always the same binary. Doesn't matter. And that's like a true, like, really important concept in distributed systems, right? And I think that's, it's kind of one of those things I think is actually really, really important. Now, one of the questions came in, how compatible is this with, Postgres command line, Chris?
Yeah, it's very similar. So I can even bring up the command line here. So if you're familiar with, Postgres, actually I'll connect to node 1.
There we go.
Yep, I'll go CockroachSQL, host equals localhost. Forgot my one more flag. And Yeah, so if you want to do, show tables, or if you need help on a particular command, the syntax is very similar. Now, we don't support every single Postgres item that's out there. There's a few things like stored procedures and triggers that we don't support, but for a lot of those features that customers are looking for, there's ways that we can support triggers through using our change data capture option. Sometimes folks can move their stored procedures into microservices. So we don't support everything that Postgres supports, but the Postgres wire compatibility is pretty spot on.
Cool. What happens when 2 nodes go down and say in a 3-node cluster? What happens to the database? Does it stop accepting connections? How does it gracefully handle that, Chris?
Yeah.
I mean,
so
in the event that 2 nodes, that's a tough one, right?
Yeah. So that's actually a tough one, right? If you have a 3-node cluster and you have a 2-node failure, what's going to happen is you're going to lose quorum. You're not going to lose the data, but you are going to lose quorum. And what happens is those ranges are going to sit out there. Our support team is very good at bringing those databases back up to health. But if you really want to prepare for resiliency, as Jim mentioned, you're going to want you're going to want more nodes. You might want 5, with a replication of 5 if you want to make sure you can fail 2 nodes. So anytime you're designing a distributed system, especially with CockroachDB, you really want to think about your resiliency factor. What do you want to survive through? So, you can certainly set up Cockroach with, with the 3-node setup, as long as you want to be able to tolerate only a single node failure. That's the best way to think about this. Like I said, you won't lose data,
Right.
But the data won't be accessible because we don't have a way of doing quorum reads and writes.
Exactly, and I think that's actually pretty important. Again, I always think about, usually with the database, I'm thinking about the logical model. You kind of got to think about the physical model of like where the data is going to be, what you want to survive, that sort of stuff, right? And I think that's like one of those key questions that's a little bit different about this than a typical database, right? And I think, going through that with customers, we talk about, I think on the website, Chris, we call them topology patterns, right? I think that's what we call that in our docs.
Yep.
And I think there's a whole bunch of, And so we walk through that with people, like how to configure the database. I've worked at a couple of pretty cool companies. I've never seen documentation as good as ours. And I'll just say that not because I love my documentation team, but we get a lot of comments. Like there's a lot of really good information about how to configure the database to survive these things in our docs.
Yeah.
Another question, Chris, and I'm just doing QA right now, you guys. I'll come back and finish up with transactions at the very end. How does bandwidth work for synchronization, right? So I have, replicas, I'm writing data in triplicate, right? And so for each replica set, let's just say I'm in a single region, there's data that's being written in a single region, but what happens when it's like cross region? I mean, how efficient is it? Is there cost associated with that when you're, let's talk about single region and then multiple region in terms of those sort of network effects.
Yeah, so great question. So anything in a single region is pretty straightforward, right? So we have a chart here in the admin UI that shows the latency between the nodes. So you can see here the latency is really low, right? Because these nodes are all close to each other. They're in a single region. So you should expect, reads to be a millisecond or less and writes to even be 2 milliseconds or less. It should be very fast. Once you start getting into geo-distributed clusters, you definitely have to, you're constrained by speed of light. There are a lot of things that we've built into the database, such as parallel commits and so forth, that allow you to do a single round trip for a particular write transaction. So that's really, and it's a 2-phase commit. So it's a really fast way that we could do writes, even though their latency between the regions might be, somewhat far. You might be going from the eastern part of the US to the western part of the EU. And you're bound to there basically by the round trip of speed of light. So yeah,
right.
Anytime
And Chris, every node can accept a write. This isn't like Aurora where there's a write node and it's in a region and you're kind of stuck with that one write node. Every single node is an endpoint. Every node can take a read write. It comes back to like the atomic unit. Everything it's all like we were talking about the UI, right? Like every node is the same.
Yeah, that's a great point, Jim. And you can be really particular too, as far as where you want to pin data. So you can make your reads and writes very low latent if they're being utilized in that particular locality. So yeah, great point, Jim.
But yep, and so all this stuff, I mean, you think about database, think about network diagnostics, would that be in a normal database? You know, that's not something that I would think about to be in a UI for a DB, but it's actually really critical when you start thinking about a distributed database. And so we actually include all of that. It's kind of table stakes to what we're doing here. So I've gone through a fair amount of the questions that were in the chat. I'm just going to jump back into just to talk about geo-distributed application. So the last thing I did want to talk through is, you know, Chris talked about being geo-distributed and how do we actually take care of transactions, right? Because if we're going to write data in triplicate across the cluster, well, man, like I got to ensure that that stuff is consistent, right? And so we do implement ACID. I mean, when we think about the I in ACID though, we're real heavy on the whole, you know, serializable isolation. And so we've actually implemented that for a distributed system. So we're pretty excited about that. And so I just want to go through kind of how that works as well. Really quickly, this is I'm going to give you the best case. There are a lot of use cases, a lot of like corner cases here, you know, multi-phase transactions that deal with like 15 tables. It gets really complicated. And our team has done a really good job about actually re-architecting the execution layer of the database to take care of these things. But let me just show you just like some really kind of core concepts of what we actually had to deal with here. Let's just do an insert into the togs table. I'm going to take 2 records and I'm going to insert into this hypothetical table. Now, the leaseholders here are those ranges that are will have a heavier outline, that gray outline around there, right? And so every SQL statement in a database actually gets broken down into multiple different transactions, right? And so in this case, the first transaction is begin transaction, which says, hey, I'm going to start this now. And then the second transaction is write. So I'm going to write Sunny. The first thing I'm going to do is I'm going to find the range, the leaseholder for the range that I need to write that data to. It's on node 1. I'm going to tell that node, okay, great, I'm going to do this. It's going to append a record that basically just says, hey, I have a transaction and it's pending. So right now I've got this range, and so nobody can really do anything else, like, because I'm going to do some work here. So it's going to be pending, and what it's going to do is it's going to say, I'm going to temporarily write this data in, and I'm going to go tell the other replicas of this data that live on other nodes, like, hey, temporarily write this in, okay? And so they're going to go ahead and do that. And it's going to, like, one of those nodes is going to return back an acknowledgement, maybe before node 4. Node 4 is a little bit further away. And basically at this point, I have quorum on the first part of this data, of this insert, right? And I've actually now, I can actually wait for this thing. Okay, the app comes back. The transaction now is also going to say, hey, wait, I've got to write the second row, and that's going to go into the second range, Aussie. And I'm going to write that record. It's going to go do the same thing. It's going to say, all these records at this point are kind of like penciled in. That's why they're all yellow. Now what happens is one comes back, and as soon as I say commit, this transaction, this temporary transaction record that I had kind of pointed out, it actually goes to commit. And in going commit, what it does is it communicates out and just says, okay, everybody commit this stuff. All of the records are now committed, and I'm going to now send back an acknowledgement back to the originator. The application was asking for this, and now I've actually done this distributed transaction. Now, I just went through a whole world of complexity in about 2-3 minutes. Doing this is not simple. Lots can go wrong, but I just want to give you, it's just a little bit of a sense about what quorum is, right? 2 nodes out of 3 actually have to write data before we can commit it. Right? So it's always an odd number in terms of replicas. You know, Chris talked about, hey, we can increase the number of replicas. That's important, but it's got to be an odd number, right? Because I need quorum. I need so 2 of 3 nodes. If it's 5, it's 3 of 5 nodes had to write that data. And so we go through that. We actually deal with that, the transactional layer, and this is how we actually are able to ensure that transactions are happening serially in the database as well. So I got 4 minutes. So Chris talked a little bit about pipeline and parallel commits. So typically when you write a transaction, there's lots of back and forth. I'm going to start this transaction. It's pending. I come back. I'm going to write Sunny. I'm going to write Aussie, back and forth. Well, what we're doing is we're actually taking the Sunny, the Aussie, and this transaction, and we're doing it kind of all at once. And we're giving it a staged, basically, status, if you will, right? And so we can actually start doing all these things all at once, and we're actually pipelining transactions. This is one of the ways in which we improve performance. And actually, we can actually send this all over in one package. So the question about network and bandwidth, all these other things, we're actually doing some really interesting things underneath the covers to actually conserve the resources that are actually utilized in the database. Now, once all those three things commit, we can actually come back and have a commit happen, and we've done this in, say, half the time, right? And so this delta between what a normal transaction looks like in a serial mode and what we're doing from a pipeline mode greatly increases the latency and what's happening in the database from a performance point of view. And so that's my last point. That was the last slide. I am at, let's see, 158 here. I talked a little bit about the requirements at the very beginning. You know, what is distributed SQL? A, it's got to be SQL. B, I hope we showed you how we can simplify this scaling of a database. I hope we showed you how you can actually have a very resilient database without thinking about other systems, and let's let the database deal with that, right? I showed you a little bit about transactions and how we can actually deal with, you know, serializable isolation. And then finally, and we didn't really get into it with the demo, but I kind of showed a little bit how we actually able to tie data to a location as well. So we are at the top of the hour. There's lots more. Our docs is a great place to get started. You know, go download CockroachDB core. It's, you know, on our website, we give you ample opportunity to go find it. You can start a cluster in minutes with Cockroach Cloud. Swipe a credit card, get a 3-node cluster up and running pretty quickly. But I would implore everybody, please do. There's a survey link here. It's cockroach/2VBW2GW. If you could, please do that survey. That would be really, really helpful to us. We'd love to get feedback in terms of, I'm going to dump this into the chat really quick here. Let me just grab this guy. I'm going to dump that into the chat for everybody so that you can actually do the survey if you like. That would be awesome if you, like, from me to everybody, to everyone, not just our organizers. If y'all could take that survey and let us know how helpful this was, it would be amazing. And then we will send out a recording and everything to everybody as well. So thank you, everybody. We are at the top of the hour. There was one last question about transactions. I will absolutely answer that. I will get that out to you in an email to this person who asked. And I believe that's the end of our webinar. So if there are any other questions, please do feel free to reach out to us. I think info@cockroachlabs.com. I'm Jim@cockroachlabs.com. Chris, are you Chris or Chris C?
Chris C.
Yeah. He's Chris C@cockroachlabs.com. So we're happy to answer these things, but any of the questions that we're here in chat, we'll make sure to get answers for everybody. So with that, thanks again, everybody, for taking your time out of the day right at 2 o'clock. Well, at least the East Coast time. Listen, have a great day. Stay safe. I hope everybody and their families are well, and everybody, their loved ones are all doing well in these crazy times. And thanks for taking the time to learn about us, and have a great day. Thanks, Chris.
Thanks, everyone.